Okay. You guys have the link and you can see the Zoom now?
Yes.
All right, so I think there's one other detail to deal with for the class. So the next class, I'm out because there was travel that I arranged before we arranged this class. And then I believe that the following Monday, there's some sort of February break. Is that correct? So we're not doing great here at the beginning because I was sick last week. We have one lecture now, and then, you know, there's travel, which I pre-committed to, and then there's a February break. Is that correct?
Yeah.
Okay, but then we should actually be able to resume with some sort of actual regular course. All right, so then I'll begin. So this class is about machine learning in the future, and I wanted to start the class with kind of an overview of how I'm thinking about it, just to give you a sense of things. And then towards the end, hopefully we'll be able to do one technical bit, which I think is kind of important for understanding how things work. Okay, so first of all, let's talk about how machine learning works at present. So at present, most machine learning is operating in a supervised learning paradigm. And what I mean by that is something like you get a large amount of labeled data. Maybe you have up to, say, 1,000 classes, which would be like ImageNet scale. And then you learn some predictor. It's typically a classifier, but it could also be a regressor. It depends on the situation a little bit. And then you use the predictor. And this is kind of the way that machine learning is affecting the world to a large extent. Almost every instance of successful machine learning deployments is using this kind of approach. Okay, so the foundation for this is a combination of getting the samples. You have to have enough samples. You need to have a good representation, and then you need to be able to optimize over that representation. It's that combination of three things which really drive supervised learning. But this is my daughter. She constantly asks me about self-driving cars, right? And the gap between supervised learning and self-driving cars is pretty enormous. And it's enormous in many ways, which I want to try to get at in the class. There's other very natural, there's other very natural problems that arise, like the who is that problem. So there's, you know, on the order of 10 billion people on Earth, and it'd be kind of nice to know who each person is. But humans aren't even good at that. It's possible in the future we'll actually have machine learning algorithms that can just recognize everyone. Right, so you could walk around, and instead of being in a crowd of strangers in Manhattan, you could be in a crowd of people whose name you know, maybe even details about them. Yeah, it's kind of scary. It's kind of cool too in some ways. It's
But cool is limited. Scary is forever.
There's lots of other scary things too. Okay, so I think adjusting to the future here is pretty non-trivial. So there's a lot of other applications of machine learning which we could imagine being extremely powerful. So for example, there's personalized medicine. The meeting that I'm missing next week is actually about that. There's an initiative to so the people are trying to tune the immune system in order to fight cancer. This is a pretty delicate process. It's very plausible that personalized approaches are going to be effective. So there's some sort of initiative around that, which is what we'll be talking about. Conversational agents is a big one. And I mean this both in a, you know, something that you chat to, which isn't all that useful necessarily, and something that you talk to and it actually does something useful kind of sense, which is which people are really working on hard. There's machine translation. Right now, I think machine translation is not really well solved. It's kind of useful if you try, but it's not nearly as smooth as you would hope for. There's personal assistance, which is not just a conversational agent, but something perhaps much more than that, because it can schedule flights for you and things like that. And so all of these applications are sort of, people are kind of worrying about them and worrying about how to do it, and it's plausible, it's extremely plausible. You need machine learning to really do these things effectively. So yeah, and here's an extra scary one. So there are a lot of jobs that are going away, or on the way to go away because of machine learning. So that's a big economic disruption. There's also a big social question about how that's handled. But it's not really the focus of this class. The focus of this class is, what does it look like as far as what these machine learning systems are going to look like in the future. Right? And I want to try to get at that as best as possible in the present. Okay, so the question is, how do you actually succeed in thinking about what these things look like? And I guess I would sort of start with supervised learning in some sense, because we know that supervised learning works, and it's very useful in a lot of situations. And now the goal is to try to extend or broaden the scope of applications of machine learning. Right? Now, when you're doing research, it's very easy to get confused, because you can start working. You can define a problem, you can start working on it, and then you can solve that problem or not solve that problem, and it may be irrelevant to the actual what gets built in the future, because it's not compatible. So there's a long history of people doing research which is just kind of not compatible with the things which are going to fundamentally work, and then it has to be discarded. So how do you get at things which are going to be compatible and which are going to be useful in the long term? So the first thing that you need to ask is sort of, what I'm working on necessary for success in the future? That's kind of a tricky thing to answer in general, but I think it's good. It's good to help focus your attention. And then you can also ask, what is a compatible solution which addresses this necessary thing? So if we take supervised learning as a baseline, then you want solutions which are compatible with supervised learning. And that's a substantial constraint. There's lots of approaches people take which are just not so compatible. All right, so are there questions about this so far?
What is meant by compatible?
Yeah, so when I was a graduate student, I worked on a paper called Graph Plan, which was about doing, well, it was probabilistic graph plan. It was about using, it was about planning in probabilistic worlds with essentially strips operators. So you have some definition of a domain, you have some goal state, you have some starting state, you want to figure out some way to map between one to the other using the operators. And maybe these operators, the twist was things could be probabilistic and they might fail.
It's like PDDL.
What's that?
PDDL logic. That's like 1972. AI.
Yeah, it was like 1972 AI type thing, but we were trying to do probabilities.
Okay.
Okay, so I mean, it worked. It was a fine paper, but it's not clear to me that approach is compatible with machine learning. So it seems plausible to me that you need an approach to planning which is compatible with machine learning, and this kind of clean, formal, logical description of operators just may not be all that compatible.
why is it like, is there a specific problem with like symbol having these predicates or?
Yeah, so from what we can tell, it's fairly difficult, so far at least, to extract a symbolic representation from some sort of neural whatever representation. There's some people who will play around with this. Maybe that will go somewhere someday, but it's not even clear that you want to do that extraction in order to do planning in an efficient fashion, right? So it may be that that extraction process is useful for communication, but maybe it's not so useful for the process of planning itself. I know that when I'm planning the trip to this room, I wasn't thinking in terms of formal specifications as far as I could tell. Instead, I was just remembering some things that I need to do along the way to alter my normal path so that I end up here. Okay. So here's my catalog of pieces to solve. And these are sort of what I consider to be necessary components. Okay, so the first one is online learning. And I think you can argue for the necessity of online learning like on computational grounds. So right now, when people are doing supervised learning, they're typically working in a batch paradigm where they just take a data set, they chew on it a long time, and they spit out a predictor at the end. Now imagine a person operating in an online learning paradigm or in a batch learning paradigm. You take all of your experience from your past life, and then you decide what to do. This is just not computationally tractable unless you're doing this in some sort of incremental fashion. So when I say online, I really mean incremental in the sense that it's okay to think about processing several examples at once, but processing all past experience all at once is, I think, is very challenging, right? So just computationally. So algorithms which support online approaches, I think, are of particular interest in the long term. Okay, so another one is representation, and so this has been a big deal of late with things like ImageNet in particular, speech recognition, to some extent NLP, although lesser, I think. Okay, so what's happening here is kind of hard to define computational complexity-wise, because there aren't very good lower bounds on the circuit complexity of functions to solve, to represent some solution. But there is this general hypothesis that if you have a circuit with n gates, that's much better than something which is very shallow in using n gates. So there's a parsimony representation which is possible using a deep circuit rather than a shallow circuit. And I think that needs to be respected. I know that some theory people, including learning theory people, don't always respect that, but this just doesn't seem very viable as a strategy in the long term.
I mean, one criticism of that, these kind of arguments on like circuit length is that we don't really know the kind of functions that we're interested in. So it may be, I mean, I remember this result by Hastad that if you have a function with n, like a circuit requires n depth, then if you have like an n-1 depth, it requires exponentially more units. But I mean,
so typically those are using monotone circuits. The circuit lower bounds that we have use monotone circuits. So there's no knots allowed in the circuit, in the gates.
Okay, I mean, the question being is like, how do we know that these worst case results are functions that we are interested in AI?
Yeah, right now I think there's only empirical evidence, which is, but I mean, the empirical evidence is fairly strong. It's certainly the case that a lot of people tried for a long time to solve vision, and the only effective approaches that we know involve relatively deep circuits. Okay, yeah?
So are you referring for the circuits as, for example, like a neural net that can be?
Yeah, a neural network is a circuit.
Yeah. But there can be anything else, or no?
It depends on how flexibly you define neural network. So when people define neural network, I think what they're really saying is something with a differential structure. So you need to be able to compute a derivative over it. And now the question is, are there circuits where you cannot compute a derivative that are interesting? I think the answer is probably yes. And we'll probably talk about that in one of the lectures. So in particular, if you want to predict one of k things in time logarithmic in k, you can't really do this in a differential fashion, because the derivative would require an order k operation. So I think representation is more fundamental than neural networks. I think circuits, I guess, is more fundamental than neural networks. But neural networks are sort of differentiable circuits as far as people tend to expand the definition. And so they certainly do play a big role. Sorry, remind me of your name again?
Eugene.
Eugene, good, okay. I'll get it eventually. Okay, so another primitive necessary is reinforcement. And this is sort of different from supervised learning, because in supervised learning, you have, this is the right thing to do. In reinforcement, you just have kind of good, bad. And I guess the claim here is that good, bad is sort of, is a more realistic real world primitive. So if you limited yourself to only, this is the right answer type of solutions, you just wouldn't be able to learn in many situations where the only feedback that you get is sort of good, bad types of feedback. Okay, so let's go on. Exploration. So maybe I shouldn't go too fast. So I'm kind of asserting two things here. I'm asserting that each of these pieces is necessary, and I'm asserting that each piece is not covered by the other pieces. Right? So if you have any doubts about that, we should discuss it a little bit. Okay, so for exploration, the claim is that if you get an infinite amount of the wrong data, you're not going to succeed. So what exploration fundamentally is it's choosing which data you get. And so in many situations, you must choose which data you get if you want to solve a problem effectively. Right? So there's several different instantiations of that, but this is the fundamental thing. Another fundamental thing is language. And there actually have been some cases where a human was raised in a language-free environment, and the results were not good in general. I mean, this is considered extreme child abuse, basically. If you take language away from what makes people intelligent, then you're left with much less. You no longer have civilization, for example. Okay, so language seems like it's a very important element. And then reasoning. So most of supervised learning is operating in a reactive fashion. You feed in features, you get a prediction. You feed in features, you get a prediction. This is not adequate to solve all problems, obviously. So you need some way to try to move beyond just a purely reactive decision. Okay, so let's debate for a minute. Is reasoning the same thing as representation? Right? Because we could imagine representations which support reasoning. So representation could support reasoning, but is reasoning just a matter of representation?
I mean, what kind of reasoning are we talking about? I mean, some kind of classification or?
So in general, I think you want to, so let's discuss the history of AI for a moment, right? So in AI land, a long time ago, people tried to solve it with logic. And this generally flopped. In contrast, in machine learning land, people were like, well, I want to be able to use some data to do something interesting, basically. And now it seems machine learning is kind of taking over AI in the sense that people say AI, they often mean machine learning, right? So what's the lesson here? The lesson here is that you really want to think in sort of a ground up fashion, because you may not get all the way to your goal, but you will make progress, and then other people can make progress. So when I say reasoning, I don't mean something super complex necessarily. What I mean is basic. I know that I left my coat over near Yoav's chair. If I want to go get the coat, then I need to get up and walk out of the room. So just being able to handle that would be a substantial increment on top of what normal machine learning can do.
Can we say that since we feel the need of interpretable machine learning, is it like because we're lacking reasoning, we have representation? We can see what the network layers represent, but we are actually not reasoning because we cannot interpret models. Like, is that the gap we are trying to bridge from representation to reasoning?
So I think fundamentally when I'm trying to get at reasoning, I'm trying to say you want to be able to integrate information from multiple sources in order to come up with a solution. And so there's the process of getting that information from different sources, like my memory, and then combining that. So representations support that process, but if your representation was not wired up to a memory, for example, then it would not be capable of handling this problem.
But one could think of representations which make the reasoning trivial. For example, it could very well have a representation which says your code is on the this and implies you have to do something. Or like in terms of neural network, you can map your representations in some space where some simple SQL classifier or something like that work. Sophisticated reasoning.
So I think in general, you could imagine trying to instantiate all the implications of everything that you know, but this would become overwhelmingly complex, and that would not be effective. So you need a mechanism for doing that reasoning kind of on the fly. And then it's not just a representation, because you need a mechanism for doing that reasoning on the fly. Anyway, this is go ahead.
Sorry, is it as well that for reasoning you need to have some history, like you need to use some previous experience, rather than for representation you just represent the current state?
Yes, perhaps. I think that the definition of state here is a very tricky thing. I was talking to Yoav and Deepinder about this. State means different things to different people, so you have to be a little bit careful when you use the word. So in particular, for reinforcement learning people, state means all the information necessary to make a decision. Mm-hmm. While for physicists, state means something about the way the world is, whether or not you actually know about it.
Right.
So if you're thinking of state as all the information needed to make a decision, then by definition you sort of have the state is everything that you need to make a decision.
Yeah. So it's a reasoning is as well about state. Right?
It's often about state. Yeah. Okay.
Fundamentally, representation is a noun and reasoning is a process. It's a verb. So it's like how you reason about something. Representation, it's a fixed thing.
Could be. So I guess there's 2 points here. I think reasoning separate from representation is maybe the most questionable separation going on here. And the other one is, it still does feel a little bit different to me. It seems like there's something different going on. And I can point at pieces of work out there that can say, oh, that's reasoning. So for example, Jason Weston has had a tutorial at the last ICML. And that was about reasoning, essentially. And it was much less about representation. Representation was as simple as you could make it and still support the reasoning itself.
Yeah, I have
Yeah.
one. So what's the difference between then reinforcement and exploration? Because for reinforcement, you would still have to explore, right? So it's the process of trying, which is basically the same for exploration, right?
Yeah, so let me defer that until a little bit later. I have a slide which addresses this, I think, pretty thoroughly. Okay, so the next one is memory. And this is something where existing machine learning algorithms just don't really have a memory, which is kind of weird. Rather, the memory is only in their parameters. That'd be one way to say it. So that means that there's no explicit recall of past events. And if you think about what you might consider intelligence to mean, explicit recall of past events is actually fairly important. So who has met people with Alzheimer's or dementia? Yeah, so a few people. It's pretty disturbing, in my experience. Talking to somebody who's kind of stateless is painful, and it's sad. But that's the way machine learning algorithms are today. Okay, so and now I think the key is how you can actually solve all of these in some sort of compatible way. And since I take supervised learning as sort of a basis, I would like an approach to solve these problems in a manner which is kind of compatible with supervised learning. Okay, so covering these topics is sort of what I think of this class as being about, how to address these kinds of problems in a machine learning approach. But I wanted to go into detail on 3 of these. So there's sort of supervised learning, which is representation, optimization, and samples. And then there's exploration. So exploration is just choosing which samples you're going to get. And then there's reinforcement. And this is to answer your question, Eugene. So how are these different? And I would say these are different because there's sort of, okay, so there's a difference in the definitions, of course, because with reinforcement, all you're really saying is that you get good or bad feedback. The form of feedback is good or bad. Now, trying to solve the problems often involves some amount of exploration, but yeah, so let's just kind of go through. So I mean this is a Voronoi diagram. So there's things in each of the individual elements here. And furthermore, I think that this kind of gives you a sense of the complexity of trying to solve, but I can't do a 7-way Voronoi diagram. At least I can't draw that. But there probably is one implicitly in what I'm talking about. Okay, so with reinforcement, there's things like Q learning. And when I go and talk to Satinder Singh, for example, he doesn't really regard Q learning as having any exploration attached to it. He regards Q learning as a mechanism for representing credit assignment. So you're taking multiple steps over some time horizon, and you want to know how good or bad an individual action is in terms of the long-term reward that you achieve.
But I mean, Q-learning does have a behavior, like it needs a behavior policy to generate the experience.
Yeah, so you typically tack on some exploration on top of Q-learning.
Oh, okay.
Like, so you say, oh, I'm going to add epsilon greedy
So by
when I'm
Q-learning,
doing Q-learning.
by Q-learning, he means like you have an access to the underlying algorithm and you just bring updates on the state action tables.
Well, I shouldn't put too many words into his mouth, but I have pushed him several times about the lack of the inadequacy of epsilon greedy, and he just doesn't regard epsilon greedy as a part of Q-learning. He regards Q-learning as a way to represent the credit assignment problem, represent and solve implicitly the credit assignment problem. Right, so the canonical thing about reinforcement is credit assignment. So if you're taking multiple actions, which one led you to crash the car, or to lose the game, or to win the prize? It may be that there are many actions that are relevant, but how relevant and how do you assign the credit to them is kind of the critical thing with reinforcement learning, at least with traditional reinforcement learning. Okay, so now there's also, between exploration and supervised learning, there's active learning. So in active learning, you have an algorithm that is trying to choose which examples to label so that you can improve supervised learning performance, basically. And so that's a substantial area of inquiry. There's also contextual bandits, which where it's a little bit of reinforcement because you could have a reinforcement feedback, but you're really trying to do exploration to optimize immediate reward, right? To learn how to optimize immediate reward. So there's exploration involved, there's a little bit of reinforcement involved, and there's also supervised learning involved because you're trying to optimize over a large policy class. So let me back up a little bit. So when you're trying to do supervised learning, I think the thing which makes supervised learning so powerful is the fact that you're optimizing over a large policy class. This is kind of consistent with the circuit versus gates way of thinking about things. You want to be able to flexibly express a large family of solutions, and the ability to optimize over that allows you to find those solutions with appropriate data. Okay, so then let's go on. So if you want to think about exploration in isolation, one model of this is bandits, right? So you're not worried about generalization or large policy classes at all with bandits. All you have is you have a set of actions in front of you. You're trying to find an individual action which is the best one to use, and you only get feedback about the action that you choose. Right? So I don't necessarily expect everybody to be familiar with everything, but I'm hoping that by the end of the class, people will be familiar with all the ideas behind these individual settings. Okay, so then let's think about exploration and reinforcement. So in between those, there's sort of markup decision process learning. So in the markup decision process, you say, oh, the world tells me its state. I take some action, I see some immediate reward, and my goal is to, and then it repeats. And now my goal is to optimize my long-term reward. Right? So there are algorithms for solving markup decision processes. These are not considered typical reinforcement learning algorithms. So these are things like E-cubed or R-max, which are typically not used, but they exist, and people have thought quite a bit about how to solve these kinds of problems. One interesting question is, why are they not used? So the setting is one where you have a state that you observe, you take an action, you see a reward, and then you see a new state, and you take an action, and you see a reward, you see a new state, take an action, see a reward, over and over again. And now the algorithms have guarantees that come with them, like the number of samples required to learn is proportional to maybe the number of states squared times the number of actions per state, or maybe even just number of states times number of actions.
I mean, anything which is number of states is just impractical for most AI applications.
Yeah, so that's the fundamental thing. So there's no generalization. So the fact that is not in the red at all here matters a great deal in terms of how useful it is. Okay, so then in between supervised learning and reinforcement approaches, there's sort of policy improvement approaches. So there's several different versions of this, but there's a kind of a conservative policy iteration. Peter Abil did a tutorial at the last NIPS talking about trust region policy optimization. There's also several versions of imitation learning, which kind of fit into this regime where you're trying to get feedback around your current solution and improve around your current solution. So these don't address exploration, except kind of maybe very local exploration, in the same sense as Q-learning with epsilon greedy, but they are addressing improving from where you are to get to a better solution to problems. And then in the middle, there's actually new stuff. We have this contextual decision process paper, which talks about how to do exploration and generalization in a reinforcement setting. So that's something which just came out last year. Okay, so are there, yeah?
I have a question. So,
Remind me of your name, please.
I'm Ramtin.
Ramtin.
Yes. Before this class, if you had told me like where should I put bandits, I would have put it between reinforcement and exploration. This might go back to Eugene's question. Is it because we don't put it in reinforcement only because the state is not changing? Because we're getting some feedback.
Yeah, I think you're right. So you do get kind of a reinforcement feedback. So it should at least be on the border with exploration. So I think that's a good observation. So the reason why I didn't put them, so I was thinking about reinforcement as credit assignment. And there's no credit assignment issue with bandits. Or the credit assignment issue is kind of trivialized. So when you go and you talk to reinforcement learning people, they like to poo-poo bandits sometimes because there's no credit assignment problem. In the regard, credit assignment is a central problem of reinforcement learning. But I think it's a little bit of a limited viewpoint.
Have people shown that epsilon greedy is suboptimal? I mean,
Oh yeah, epsilon greedy is known to be suboptimal in several ways.
is there like an optimal exploration policy that even for like some very special case?
Yeah, so for bandits, people have certainly looked at a lot of different exploration policies. It's a very simple problem. And there's no clean answer because what do you assume about your bandits? So if you assume nothing, then maybe there's an answer. But if you assume that, like so for example, kind of sort of in between contextual bandits and bandits, there's kind of linear bandits, which is a particular kind of context and assumption about how the reward structure works. And there, you're assuming some sort of linearity to the reward, you can get better results because of that additional assumption. So what I'm trying to say is the if varies so much that the thens cannot be compared across many of the different theorems.
But it's more than that. It's more like conversion versus frequentist. In frequentist, we have no notion of something. We have some notions of optimality, but usually we don't apply them bandits. If you put a prior over everything, you always have the Bayesian optimal procedure. It's just really difficult to compute.
That's true. There's different notions of optimality, and that also
no
levels
notion
things.
of optimality usually. Usually in the bandits, there's no optimization problem we're trying to solve unless we assume the prior.
So one notion of optimality has to do with the gap between a lower and upper bound in a regret measurement, right? So how close can you, so there's like a lower bound in terms of regret, which says that here's a family of problems for which no solution can solve things very effectively. And then you have an upper bound, which is of the form, I can solve all problems with this amount of regret. That's not typically, there is a gap in the constants there, so that's not a perfect notion of optimality, but it seems like it's decent in situations. Okay. Other questions? Okay, so I wanted to switch gears. So, right. Okay, so what I wanted to do for the rest of this lecture is just discuss the foundations of why this works, of why batch supervised learning works, because I think understanding that foundation is very helpful in being able to extend that foundation to new settings. So this is batch supervised learning, and the success is basically a matter of representation, optimization, and having enough labeled samples. So then the question is just, okay, so representation is complex, and we'll discuss that a little bit in other lectures. Optimization is complex, but as far as labeled samples go, I can actually show you why labeled samples are effective in a pretty strong but very basic sense. So I wanted to go through that, and this might be too easy for some of you, or it might be too hard, I don't know, but I'd like to get a sense of whether or not you like it. Okay, so I want to try to talk about the simplest model of generalization. How do we know that we're going to perform well on a test set? Okay, so I'm going to think about some input space, X. This could be features. I'm going to think about maybe a binary output space. It could be multi-class, doesn't really matter, but let's just think about binary for here. I'm going to think about classifiers. Then I'm going to make one assumption. I'm assuming that all of my samples are drawn independently from some unknown distribution. Okay. So then I have a sample which is drawn independently from D to the M. All right, so then what can I do? The thing that you care about here is for some classifier C is its error rate. So the fraction of times that the classifier predicts incorrectly. So I'll call that C sub D. But of course, we're not assuming that we know what the distribution D is, because that would be assuming that we can solve the problem perfectly. Instead, all that happens is that we see the sample S. Okay, so then what can we actually know? Well, we can know the number of errors that the classifier makes on our data set. So that's what C hat sub S is. So the hat just tells you this is an empirical quantity that you can observe, and it's just a function of the classifier and the data set S. Okay, so then the question is, what is the distribution of C hat sub S? So this C hat sub S is a random variable. You're drawing samples from D. You get a bunch of samples. On each sample, you either have an error or you don't have an error. What is the distribution that's created? Somebody, I think, probably knows this. Let me go here. This is a picture which shows the distribution created as a kind of varying my observations. And so the red is kind of the true error rate, the C sub D, and then it induces a distribution over your observations, which is given by the black. So in particular, if the true error rate is near 0.5, so you're in the middle, you get something which kind of looks like a Gaussian, but with a step function. And if you run over towards the edge, it becomes very extreme, like this.
does it mean again? Is it error rate?
Yeah, so we have, let's go back here. See, I'm drawing essentially the fraction of times that C hat sub S divided by the size of S. So just the error rate, the portion of your samples which have an error as a function of the true error rate, which is C sub D. It's the probability that an example errors. So the red is the true error rate, and at different true error rates, you get different fractions of the times that your observed error rate is 0 or something larger.
Binomial. So you have k samples.
Yeah.
And let's say like k of like some I of them are wrong. The probability of I of them wrong would be Ct to the power I.
Yeah.
The remaining one correct would be 1 minus Ct to the power n minus I.
That's right.
And then you can choose them in MCI ways, and then you just.
Yeah. So binomial is the distribution. So this is a binomial distribution.
Is it what is x? Axis?
X is the number of errors. And Y is the fraction of times that you observe that many errors.
So when you move it to the right, you will not get a lot of errors, right?
If you move to the left, then you have very few errors. If you move it to the right, then you have very many errors.
All right.
Right? And at the extreme, you have all errors. So yeah, if the probability of an error is 1, then you observe all errors empirically.
And what's the y-axis?
The y-axis is the fraction of times you observe that error. So if you, it's hard to do with your eyes, but if you add up all the black, it adds up to 1 vertical black line in terms of the area. So the area is constant because I'm counting the number of possible events.
But when you move it to the left, you will get less or the same amount. You get the same amount, right?
Yeah, the same number of outcomes occurs because we're just counting outcomes, and we're asking how many errors are in each outcome, and then we're adding up all the outcomes with the same number of errors and plotting them on the same vertical stripe. So we're just drawing the binomial distribution. Okay, so it's important to understand several things here. One of them is that, it looks like a Gaussian when you're here. So when your error rate is large, it's going to behave like a Gaussian. So a lot of statistical heuristics involving standard deviations work reasonably well. But when you come down here, it starts looking less and less like a Gaussian. And that's fairly relevant actually for machine learning because you're trying to minimize the error rate. Okay, so the basic observation is that the distribution is a binomial. Let me go back for a minute. Are there any other questions about this graph?
What is the green line?
I'll get to that in a moment. But the truth is, the green line will be an observation. And then the red line will be a bound on the true error rate rather than the actual true error rate. Okay, so this is the distribution. This is how a binomial is defined. You have some number of heads for your coin. The bias is the true error rate. You have the probability of that type, and you have the number of ways that can occur, which is what the M2's K tells you. Okay, so this is the probability of having K heads with n flips of a coin with some bias C sub D. Okay, so now this alone isn't quite what we want. What we really want is to think about as a cumulative distribution. So what is the probability that you have k or fewer heads, or k or fewer errors, given the true error rate? And so it's just adding a sum from I equals 0 to k to everything. So that's it. If we go back to this graph, what that means is I'm talking about doing some integral of a portion of the curve. Okay, so then this alone is not quite enough, because this the problem is that computing this integral requires knowledge of C sub d, because that's an argument to the bin function here. You don't know what C sub d is. So instead, we need to have a function which depends upon what we can observe, which is what C hat sub s is. So you can invert this. You can say, what is the largest true error rate, P, such that the tail has mass at least delta? Okay, so now we can go and look at this. So I set up the tail here to have mass 0.05, which is a common choice. So if you look at the tail, the part to the left of the green line, it's always a small fraction of the total mass, right? And then I'm computing what is the largest true error rate, which is what the red line is, such that the tail, the part to the left of the green line, has mass 5%. Okay, so we're almost there, actually. So what's happening is there's an error rate. The error rate defines a binomial distribution, and then we can ask ourselves, given my observed number of errors, what is a bound on the true rate of errors? Right, so that's what this test set bound theorem says. The claim is that for any classifier and for any distribution, for any choice of delta, this holds. So the true error rate is bounded by the output of this bin thing, which is used just observed quantities as arguments, with high probability, probability 1 minus delta. Okay, so this is very powerful, because this says that if you do machine learning, as long as you have a test set, you can just check to see that you in fact succeeded, you generalized, that you will perform well in the future. So that's very good. It's still not quite enough to tell us why supervised learning is useful. It says that you can measure and you can check to see if you have succeeded. It's not the same thing as saying that you will succeed. And we can go one step further to prove that we will succeed. Okay, so one step further is this Occam's razor bound. So this is slightly more complex. We have a set of classifiers. We're going to put a prior over the set of classifiers. So we're going to say the probability of classifier 1 is 0.1, the probability of classifier 2 is 0.2, and so forth. So we have a distribution over those classifiers which sums to 1. And then the claim will be that for every choice of prior, for all possible distributions, for all probabilities of bound failure, the probability with respect to a random draw of a sample, that for all classifiers, the true error rate is bounded by this bin bar thing, except now we have delta times P of C instead of delta as an argument, is greater than 1 minus delta. So it says that for every classifier in a large set, you will have a good estimate of its true error rate. For every classifier which has a significant value of PFC. So in particular, if you choose PFC to be a uniform distribution over a finite set of classifiers, then PFC would be 1 over the number of classifiers. And then you would just plug that in, right? So it's a little bit hard to know what then means. So people often use various bounds. One of them is this corollary. Would be called the turnoff bound. So there's a log, if you look at the turnoff bound, it's a log 1 over the probability of the classifier, which means that if the probability of the classifier was 1 over the number of possible classifiers in some set, then this would be the log of the size of the set.
When you do probability over classifiers, you mean that you're putting probability over all the possible weights that can be assigned, for example?
Yes. Yeah, so we're thinking about linear classifiers. We're saying we have a distribution over all the possible assignments of parameters, of weights in that linear classifier, or with a neural network. Yeah, so every specific set of weights has a different distribution, a different probability, right? Okay, so but the important thing here is that you have that logarithmic dependence. And that means that you can basically take the number of bits used to specify your classifier, and you can plug that in here.
If you have a very big classifier, it's essentially useless.
Well, you have a very big classifier compared to the number of samples. So this is the description length here divided by the number of samples. And if you start adventuring into learning problems where the number of parameters far exceeds the number of examples, you can in fact go wrong. Sometimes you don't, but the foundations of supervised learning become weaker when you get there.
Is it for only a random distribution, like when we feed it randomly?
No.
Or that
No.
doesn't matter?
Oh, the only thing that's being randomized here is the distribution S. Right. So the samples. The P of C, you don't have to be drawing from the distribution over classifiers. This is something which holds over all the classifiers simultaneously.
I'm thinking about S. So
Oh
S
yeah,
is-
so S is random, and that's important for being able to prove things. Yeah.
What does the probability of classifier mean again? Like, is the probability that the algorithm will give this classifier?
No, it has no meaning other than what's stated in the theorem. So the meaning is just you need to specify P of C up front, and then I will have something which holds, but it holds weaker for things with a smaller P of C. So the theorem holds for every classifier, but some of those classifiers, most of them, will have a probability which is incredibly close to 0. Right? Or maybe which is 0. In which case, the theorem is vacuous for them. Does that make sense?
The probability of odd words for event.
So we're not thinking about a process. We're just thinking about the axioms of probability. Every element has a probability which is greater than or equal to 0, and the sum of the probabilities of all the elements is equal to 1. That's the only thing that I mean here. Right? And because, so if you have any description language for describing a classifier, the description has some number of bits to describe any classifier. So you can choose the P of C to be 2 to the minus description length. And then that will be something which sums to 1 or maybe even less, which is fine.
So a lot of the neural networks, they're like using 80 million parameters, and I'm quite sure their samples that they're training on is much smaller.
Not much smaller. It can be a little bit
It's only
smaller.
1 million.
Yeah.
And so would you say that it's because the P of C is not uniform there, and they have a way of like the learning algorithm is good at like getting at the right solution and like instead of wasting time on like.
Yeah, so there's more advanced bounds, which take into account the fact that if there are multiple equivalent solutions, all of which work equally well, then your number of samples required is smaller. So this would be something like the pack-based bound, for example, right? But in general, these bounds, I think, provide a good understanding about why it's possible to do supervised learning. But they're often loose at a factor of 10 or 100 level. So you can often get by with fewer samples than these bounds would imply.
Are we going to cover packed learning in this?
I wasn't planning to do it beyond this lecture, but I haven't entirely determined what the course will be about yet. Okay, so just to keep us honest, I wanted to go through the proof, and the proof is actually just this slide. Okay, so we have the test set bound, which says that for any classifier, the probability that the true error rate is less than this bin bar when we plug in delta times P of C is greater than or equal to 1 minus delta times P of C. Okay, so then what we can do is we can say, we're going to negate that, and that's just the standard formula for negation. And then we're going to say, oh, well, now we can use the union bound. So the probability of A or B is listing to the probability of A plus the probability of B. Okay, so then we can apply that repeatedly for every single classifier. And now the for all becomes exists inside when we apply the union bound repeatedly. And then you negate that again and you get the proof. So this is the most elemental description I know of for why generalization is possible, why supervised learning can work. It works because you have a large family of classifiers that you can compete with on this sort of logarithmic basis, right? So the number of things that you can choose amongst is exponential in the number of samples. And now as long as you have a reasonable representation which has a good solution somewhere, and you can optimize over that representation, you can succeed.
So when the delta is lower, we'll get the better probability of getting the error rate small, right? That's what we want. When we increase delta, right?
Yeah. So let's go back to here. So here delta is 0.05. If I made delta larger, then the green line would become closer to the red line.
Mm-hmm.
Right? And by the way, the blue line here is what happens when you use the square root approximation. And so you can see the blue line is somewhat loose. It's particularly loose when you're at 0 error rate. It's not so loose when you're at an error rate near 0.5.
And we want to get observation close to the error bound, right?
Yeah, so there's some sort of inherent looseness here because delta is not 1. But neglecting that issue, you would like your empirical error to be as close as possible to your true error. And as you get more and more samples, we can go back to the bound, you can see that's what happens. This quantity here gets smaller and smaller as the number of samples increases. So I think we're about done. So I'll be seeing you guys in 3 weeks. In the meantime, if anybody has questions or comments, email me. I'm jl@hunch.net.
Is there any reading for next lecture?
Good question. I'll think about that and get back to you.
What's that good book on like
On the bounds,
like would it be the
I wrote a tutorial once, which may be a good thing to take a look at.
is the Vazirani book any good?
What's that?
The Vazirani book.
I think the Vazirani book probably covers not the elemental version, but the version where they do sample complexity bounds.
You can make